Hey guys, Mr. Betts here. Let's take a look at a couple of fairly straightforward examples where we're going to be using related rates to solve the problems. So the first one here involves the example that I gave in the introduction video for this unit. So we have a spherical balloon and we know how fast air is being pumped into the balloon. And so we want to know how fast the size of the balloon measured by the radius of the balloon is changing at a certain point. So to start with here, we want to look for context clues that tell us what kind of rates or derivatives we have in this problem. So the first thing here is we have air being pumped into a balloon. So it's being pumped into at a rate of, well, this is a dead giveaway here, at a rate, that's a rate, we know that's a derivative. We also have a clue with the units, should be cubic centimeters per second. So the units are a rate that give us a change in volume with respect to a change in time. Another clue there. So this one's pretty straightforward because we don't have to dig too deep to figure out that this 10 here is going to be giving us the value of a derivative in this problem. So what we need to identify that as is what derivative. Like I said, the units are a big hint here, cubic centimeters per second. Well, cubic centimeters are a way we measure volume, so that's a change in volume. Seconds are a way we measure time. So this derivative here is going to give us a change in volume with respect to time. So even with the context clues that air is being pumped into a balloon, if you didn't realize that was actually affecting the volume directly, the units tell us that that is a change in volume with respect to time. It's not a bad idea in these related rates problems to include units. So I'm going to do that here because by including units, I can make sure that my answer has units that make sense in the context of this problem. So we know that dV dt is 10 cubic centimeters per second. It looks like that derivative is staying the same because it says that's just how fast air is being pumped in. So that's a good start for us. Now the question is asking for the rate that the radius is changing. Well, the rate that the radius is changing, specifically it's going to be increasing, which makes sense because air is being pumped into the balloon. That's going to be given by dr dt. So dr is a change in the radius, dt is a change in time. So this tells us how fast the radius is changing. And it doesn't say it in the problem, but the units that we would expect to get here would be units on the radius, which would be centimeters, and the units on time would be seconds. So the units we should get on a change in the radius is going to be centimeters per second. So once I know those things, I need some sort of relationship between V and R. And from geometry, which I know might have been a few years ago for you, you should know that the volume of a sphere is 4/3 pi r cubed. So that relationship tells us for any given radius, what's the volume? And in particular, we want to know how fast things are changing. So we're going to do some calculus on that. We're going to do implicit differentiation and take derivatives with respect to t. So we get dv dt on the left side equals 4 pi r squared dr dt. So again, that's using implicit differentiation with respect to time to take the derivative here. And then at this point, we just need to plug in what we know to solve for what we don't know. So we know that dV dt is 10 cubic centimeters per second. So I can plug that in over here. And I'm going to keep the units on here. Numerically, it should work out even if we don't include the units here, but I want to make sure that we're getting things that make sense. The radius, this is given to us here, and this is something we need to be kind of careful about. A common mistake is to take this 10 here, this 10 centimeters, plug it in for the radius here, and then do the calculus. If you think about what that would do, if we plug in the 10, then this right here is going to be just some constant, and when we take the derivative, that's going to be 0. All right, since the radius is changing, I don't want to plug in the value for the radius until after I've taken the derivative. So the 10 centimeters can go in where the r is, and that's squared. and then times dr dt, which is the value that we're trying to find. So just solving for dr dt, we're going to divide by the 4 pi times 100. So we're going to have 400 pi square centimeters. I'm keeping with the units here just to make sure things are the way are going to work out the way they're supposed to. So we're going to have 10 cubic centimeters per second divided by 400 pi square centimeters, because the centimeters got squared here. And that's going to equal dr dt. And just doing a little simplifying, the 10 is going to cancel with the 400. Centimeters squared are going to cancel with square centimeters there. And we end up with then 1 over 40 pi centimeters per second. And we can confirm here that the units that we got match the units that we were expecting. So this answer seems like it would make sense. So again, as the volume changes, then the radius is changing. And so a small change in volume is going to affect the radius in this way. So when the radius is 10 centimeters, the volume is increasing by 1 over 40 pi centimeters per second, which is not very fast. Okay, second example. We have a right triangle, and we have some things changing about that right triangle. So the base is increasing. So the length of the base is increasing. That's a pretty straightforward keyword there. At a rate, also a keyword there. And then centimeters per minute, that's a giveaway there. So lots of stuff indicating that this is going to be a rate. This is how fast the base is changing. So I'm going to call that dB dt. So B is going to represent the base of this, and dB dt is going to be 4 centimeters per minute. Then we have the height changing. So the height is increasing at a rate of 5 centimeters per minute. So we'll call that dh dt, and that's going to be 5 centimeters per minute. Now, I want to point out here that both of these quantities are increasing, which is why the derivatives are positive. If the problem had one of these decreasing, let's say that the height was decreasing, then we would end up with a negative 5 instead of a positive 5. That's not the case here, but we want to be careful that when things are getting bigger, derivatives are positive. When things are getting smaller, derivatives are negative. So then the question says, how fast is the area of the triangle changing? So we want to know what dA dt is when both the height and the base are 20 centimeters. Again, the height and the base are both changing. So this is going to be at some particular moment in time. I don't want to plug that 20 centimeters in until after I've taken derivatives. Otherwise, the constant that I get is going to disappear by taking derivatives. So I need a relationship between 3 variables this time: the base, the height, and the area. And this is one that's pretty straightforward. Hopefully you're familiar with it. Area of a triangle is 1/2 times base times height. And I want to know how fast things are changing. So I'm going to take the derivative. And I'm taking the derivative with respect to t. So we get on the left side dA dt equals, on the right side, we're going to do product rule. So product, I'm going to do 1/2 b is the first and h is the second. So derivative of the first, derivative of 1/2 b is going to be 1/2, but that's with respect to b. We're taking the derivative with respect to t, so I need to multiply by dB dt. All right, so that's the derivative of the first times the second plus the first times the derivative of the second, and the derivative of h with respect to t is going to be dH dt. Okay, so kind of a new idea here where we're using implicit differentiation with respect to a different variable, but we're really not changing anything that we were doing with implicit differentiation from the last unit. At this point, we have all the information we need in this equation. We just need to plug stuff in. So we're going to plug in, we don't know what dA dt is. That's what we're looking for, so I'll leave that. By the way, dA dt, we should expect units to be area measured in square centimeters because lengths are measured in centimeters, and time measured in minutes still. So we should expect an answer in square centimeters per minute. So let's see if we get that. So we have 1/2 dB dt is going to be 4 centimeters per minute times h, and h we know is going to be 20 centimeters, so is b. So at this moment, the base and the height are both 20 centimeters. So this will be 20 centimeters plus 1/2 base is 20 centimeters times dh dt is going to be 5 centimeters per minute. And really, this is a numerical answer. And if this were a free response question, you could actually just box this. I would say that if you were going to do that, we should take the units out from the middle here and just say that the units are going to be square centimeters per minute. I'm going to assume this is a multiple choice problem and we have to figure out what the actual number is. So let's do a little bit of math here. The first one, the 1/2 times 4 is going to be 2, and 2 times 20 is 40. So we're going to have 40 for the first term. Second one, 1/2 times 20 is 10. 10 times 5 is 50. So we're going to have 40 plus 50, which is 90. And each of the terms is going to be centimeters times centimeters divided by minutes. So they're each going to be square centimeters per minute. So at this moment, when the base and the height of the triangle are both 20 centimeters, the area is going to be changing at a rate of 90 square centimeters per minute. Now, in problems like this, we actually should write out our answer in a way that directly answers the question. This is the answer to the question. It's changing 90 square centimeters per minute. It doesn't really tell us whether it's changing in a positive direction or a negative direction, even though the 90 is positive. So we're going to write out our answer here. So the question says, how fast is the area of the triangle changing when the base and height are both 20 centimeters? So we're going to say the area is, we want to say increasing or decreasing or some synonym of that. Since the 90 is positive, it's going to be increasing. And that should make sense because both the height and the base are getting bigger. So that should make the area bigger at a rate of 90. So even if the area was decreasing, we would still use the absolute value of our answer here. And we want to make sure we include units. So square centimeters per minute. So when we're giving answers like this, we want to give what the number is, whether that number indicates increasing or decreasing, and the units that would be on that answer also.